Thank you, and good afternoon. My role as an engineering manager at Microsoft is to defend the Windows infrastructure that hosts SharePoint Online and OneDrive. And this means I have on the order of 100,000, 150,000 Windows machines in a network that I need to defend. And I'm here to share with you today some of the mistakes that I've made, the things that I've tried that didn't work, and some of the things that seem to be working now. And I want to be completely transparent with you today so that you can learn from my failure and maybe replicate some of my success. So with any talk, it's important to start out with what we're trying to accomplish, right? In Office 365 and in SharePoint Online specifically, I want this to be the safest cloud for your data, whether that is your customer data, your intellectual property, or maybe you're a service provider and this is someone else that has trusted you with their data. But yet, when I look at the threat landscape, I see that other cloud service providers like me are experiencing intrusions, are being breached left and right. And I don't believe that this is because they're negligent or because they're not investing in the right place, but because of something that we call the defender's dilemma, the asymmetry between the adversary and the red team or the blue team, the network defender. Right? The notion of the defender's dilemma is that I, as a defender, need to be 100% perfect at all times at defending my infrastructure if I want to keep an adversary out. But my adversary can wait weeks, months, years for me to slip up. And because I'm a human and my organization is full of humans, we know that that will happen. And so that leads me to a conflict between my business goals of having the safest infrastructure in the world and my reality, which is that I am going to experience a breach. It's a matter of when, not if. So my value to my organization is in building a capability that we call adversary resilience. Right? And this is the notion that when a breach occurs, I can detect and evict that adversary before he has had the opportunity to access customer data. If I can deliver on that promise, then I can experience an intrusion without it turning into a breach, without impacting my customers. As Mark Rusinovich showed this morning, the notion here is that our blue teamers, right, as network defenders, we have a kill chain that we need to go through, just like our adversary does. We need to get that data from our environment, get it through a detection system to classify it as good or bad. We need to alert on it, get it in front of our defenders, make a decision, come up with a remediation plan and execute on it. And if I'm faster than my adversary is at completing his red team kill chain, then I can disrupt this attack. So when we started this 4 years ago, we thought this was going to be really easy. We discovered that we had a Microsoft scale MapReduce system called Cosmos at our disposal. We have petabytes of security event logs being uploaded to it every day. And so we said, you know, I have all these logs. I bet I just need to write some scripts. I'm going to do some queries, maybe filter some things out, and I'll be done. And I can move on to solving some other really difficult problem. And so what did we do? We started with the data that we had. And we said, well, I have lots of failed logons. They're failed, so they must be bad. So I'll do some pivoting. I'll make Power BI charts. And the only thing we ever learned was that sometimes our engineers type their password in the username field. And when they do that, we discover that their passwords are terrible. So this didn't really teach us anything. It didn't help us achieve our goal of detecting an adversary. Right? This was kind of just a waste of time. So the next thing we thought was, well, maybe instead of looking at failed logons, I want to look at successful or normal activity, but the normal activity that's anomalous, right? So not failed logons, but successful logons. Let's look at process starts. So we started to kind of filter out the things that we knew were normal. Because we own the infrastructure, because we are the team that designs and administers the interface, we can go look at our source code. We can talk to our engineers and learn which processes are supposed to execute. We know which service accounts are supposed to be switching to other accounts to impersonate users. For example, during maybe remote PowerShell execution or ASP.NET impersonation. And so we took all of our Windows security event logs, had engineers painstakingly filter out the things that were normal, and we made dot plots, right? And as we started to build up these dot plots, we went from 10 minutes of triage to 15 minutes a day of triage to 30 minutes to an hour and 15. And eventually, my team sat down and they said, this is really neat. You used recommendation algorithms to try to look for processes that were unlike what other people like you ran, but ultimately, we're kind of just playing spot the dot, right? Somewhere in this graph is a red teamer or an adversary, a real intrusion. But I can't tell the difference between the 364 days out of the year where this is entirely benign and the 1 day a year where one of those dots is malicious. So let's stop fooling ourselves that we can find Waldo on any given day. We need to do this work with integrity. So we thought, let's get our engineers involved. If we see anomalous activity on one of our engineer accounts, why don't we send that report to the engineer themselves? And we crafted this really carefully. We didn't want to use red. We didn't want to use spooky language. We didn't want our engineers to think that they had done something wrong. And this actually worked pretty well. We got good click-through rates. People would legitimately click no if they didn't recognize their activity, and that would page a security engineer, and we would get involved to start doing forensics. And so we moved on a little bit and said, well, this is working. Let's try machine learning, right? That's the next sophisticated way to detect anomalies. So we built a Markov chain model looking at the sequence of processes being executed on our machines. We took each logon ID, arranged the processes in that logon in order, and then looked at the frequency of B following A and C following B. And what we learned when we showed that to the user was that our engineers don't actually understand what's happening when they're administering the service. Yeah, maybe they know that they ran PowerShell, but they don't know what that script did that they just executed. And that was frustrating to us because we did a bunch of work to present them a nice, pretty view, rather than showing them what the Markov chain model really looked like. But aside from that, we actually had a bigger problem. What's the thing that machine learning researchers love to tell you when they're proud of their model? You've given them a labeled data set or a data set from, let's say, a pen test, and they come up with a model and they say, look, adversary activity is in the top 1% of results for this span of time. We got really excited about that because we were new to this and data science projects were new to us. And so we said, well, that's cool. Well, let's run it over a 10-day period. And the data always looked like this, right? In Office 365, we're constantly deploying new infrastructure. We're lighting up new features. We're deploying new machine roles, refactoring the service to reduce the amount of time and energy and money that it takes to run the service because we want to be more efficient. And the model can't tell the difference between a legitimate change to the service behavior or an adversary introducing an anomaly. And so we kind of gave up on machine learning for a little while, right? We kept looking at this data and it just wasn't working for us. And my mentor, John Lambert, pointed out that really what was happening was that we had a ton of data, but none of it was the kind that we actually needed. So we'd spent all of this time taking the gift that the Windows Security Event Log gives to us. And if you're familiar with the metaphor or the children's story, the fairy tale of the princess and the pea, somewhere there's an imperceptible little change deep inside of our environment. And we're many layers away from that change, and we're looking to try to find it, right? We were looking at logons, and then we were doing machine learning on logons, and then we were doing crowdsourcing on machine learning on logons. Maybe we have the wrong data. So we shifted our tactic. And instead of looking at the data that we have, we started to look at who our adversaries are, who our threats are, who is going to attack us, what are their motivations, what kind of tools do they use. And so we didn't have a fully functioning threat intelligence program when I started this. So we worked with our red team and said, okay, in the red team breaches that we have experienced, how did they get their job done? Let's map that to the kill chain. Let's look at what tools, what techniques they've done, and let's try to figure out what evidence is left behind when these tools and techniques are used in my environment. So we took a page from forensic science. This is Edmond Locard, who pioneered the notion in forensics that every contact leaves a trace. The notion here is that if I'm a physical attacker and I commit a crime in a physical crime scene, when I enter that crime scene and then leave, some of me is left behind, and some of the crime scene leaves behind with me. And so as a forensic investigator, your job is to match up the evidence that you find on a suspect with the evidence that you found in the crime scene. Well, why don't we do the exact same thing in the SharePoint Online and OneDrive environments? So we started to look around and discovered that we can detect much of this activity in real time using Windows ETW. I think David Weston mentioned this earlier in his talk, but Windows is instrumented top to bottom with event tracing called ETW events. And these events instrument key Windows components like DNS, like the Windows kernel for all of the network and image load, thread activity, memory allocation. We can also look at state changes on the machine. Once I have an agent running there, well, why don't I take a snapshot of security critical registry entries and compare those hour over hour or day over day? Why don't I compare those across the other 100,000 machines under my care? I have a tightly structured security environment. My machines are grouped into roles that are supposed to be homogeneous. And so if I see not just an anomaly, but an anomaly in a registry key that I know is security interesting, then that might be some evidence that I want to look at. So here's the model that we ended up following. We have kind of three pieces to the model. On the top, I have my adversaries' tools, their techniques, their practices. We call them their TTPs. On the left, I have the ETW activity that I can get from my environment. And on the right, I have expected activity, the things that I know my service will do as it operates, or that my engineers are doing as break-fix activity. And where ETW and adversary TTPs overlap, that's the evidence that I want to pick up. But unfortunately, some of the activities that perhaps my engineers or my service accounts do in my environment, they overlap with what my adversary might do, right? Perhaps I have an engineer whose favorite way of running a script across many machines is to use psexec rather than using invoke expression or invoke command. So I need to do some work with that engineer to make more white space here. And then when my expected activity generates ETW events, and those get into my logs, then I need to filter that out. But if I'm successful at kind of integrating all three of these classes of events, then I can build a really successful intrusion detection sensor. So what we built was a sensor agent that you might think of as the precursor to Defender ATP that is specifically customized for the environment that I administer. So this sensor agent is a C# process that runs on every machine, and it subscribes to ETW events. It tells the Windows kernel, I want to read every process event, every TCP and UDP packet that you send. I want all of the DNS resolution events, all of the WinINet events. And I'm going to put those on an asynchronous pipeline that will decode command lines, maybe to a greater or lesser degree of effectiveness, thanks to Daniel's invoke obfuscation talk. I'm going to merge process and network activity to build up NetFlow on a per process basis, because ETW has the really nice property of always giving me events that are attributed back to the process that generated them. So I can see whether PowerShell, service host, LSAS, any application on the system is sending data. I can see which IP addresses it's sending it to. I can see how much traffic is being sent. I can do interesting analyses here in real time, like looking at the inter-packet timing of TCP and UDP activity to look for beaconing that might indicate command and control. After I do aggregation and filtering, I'm going to write these events back to the security event log, and then I'm going to upload those to my data lake system, my MapReduce system, where I can do queries, I can look for anomalies across my environment, and I can also output alerts. So ETW, as I mentioned, is a rich source of both security data and security analytics. So at the end of my talk, I'm going to give you a link to an open source framework that we wrote for integrating ETW into modern C++ and C# applications. For us, we had to interface directly with the Windows APIs. Those were pure C. We found them very difficult to integrate with. So we wrote a wrapper that we think will help you build your own sysmon, build your own Defender ATP, and really begin to instrument your own environment in user mode very quickly. So we've got sample code and a library that you can use there. But this is a sampling of some of the things that you can do with ETW. I think on a modern Windows 10 system, there are over 1,100 different ETW providers that give you varying degrees of instrumentation about the activity going on in your system. So the odds are that if you're studying what adversaries do, and you go look for corresponding activity in ETW, you'll be able to find sensor activity that you can use to detect it. So what that led us to then was a threefold system for instrumenting and implementing intrusion detection in our environment. On the one hand, I want to constantly be ingesting breach reports and threat intelligence, not hashes and known bad IPs, but adversary tools and techniques. I'm going to go replay those in my environment. I'm going to build detections for the ones that I can't currently detect. Next, I'm going to focus on my network perimeter. I want to know when unauthorized activity gets into my environment, maybe a backend login that came from an IP address that I didn't expect to be opened through a router ACL. And I'm going to look at outbound traffic, TCP, UDP, DNS, ICMP. I'm going to make sure that an adversary has a difficult time getting in and that he can't get out without tripping alarms. And then finally, and this is the thing that is most challenging in any live cloud service, I'm going to build greater degrees of isolation so that if an adversary wants to move laterally from one capacity domain to another domain, that's going to set off alarms because he's forced to move in a way that the service does not typically see. But the high-level takeaway for us was that we learned that it's more important for us to be able to rapidly gather new sensor data. That's actually more important than building, let's say, a real-time analysis system. Because what good is it to very quickly be able to process Windows security events if in those security events you can't actually find things that correlate to adversary behavior? So once we had the ability to quickly instrument our environment, push out new builds of our agent, get new feeds from ETW, we found that our defensive effectiveness increased dramatically. And what this has led to, as we work with our red team, as we invite them back to come do more red team engagements with us, is that we're starting to tip the tables on our red team. Rather than having just the defender's dilemma, now they have the attacker's dilemma. In order to completely evade our detections, they have to know every detection that we have. They have to find a way to accomplish that stage of their kill chain without tripping that detection. And they have to keep up with us because we ship new detections for our infrastructure on a daily or weekly basis. And the great thing about this is that I don't need to be 100% effective as a defender. For any given adversary campaign that successfully gets a foothold in my environment, I need one detection. Once that one detection is gone, my forensics starts, incident response starts, and I'm on the adversary's tail. So sometimes my red team is really proud when they can bypass one particular detection that I have. But that's okay, because they have 100 more that they still have to find a way to evade. So we're not resting on our laurels. You know, to take back to the initial concept here of adversary resilience, I've spent all of this time failing and finally succeeding just to accomplish detection in my environment. But the blue team kill chain doesn't stop with detection, right? That's only the beginning. So how can I make triage and eviction and incident response quicker? This morning, Mark Prasinovich showed you the work that my team has been doing with graphs to take alerts, combine them together, make more sense out of them so that I can both look at incidents all at once rather than isolated detections. But two, this also lets me, I think, unlock the power of real-time detection. So I want you to imagine for a moment that you have a real-time pipeline and you're sending your evidence-based detections through it. Right? You have sensors that came from ETW. Those are being maybe sent through a Spark streaming system, and you're classifying data. You're looking for things that are bad or that are security interesting. Well, what we've discovered is that almost all of these detections are low fidelity. I'm not going to call somebody when I see activity coming through WinINet. I'm not going to call a security engineer when I have a process that's beaconing to a destination or a process that's talking to a new type of destination. But if I start to see multiple signals that are correlated together across the adversary's kill chain and grouped together in the graph, well, then I think I have a real incident, not just a set of anomalous behavior. And so the combination of a real-time data pipeline and the ability to correlate activity with graphs to find related alerts and incidents are the two things that when you put them together enable me to react to an adversary's intrusion just as fast as my adversary is able to move laterally through my environment. So, okay, I find an incident. One of these turns out to be a true positive. What next? In the past, we've relied heavily on our MapReduce system. And we've thought that this was really great, that we can handle petabytes of data, that we can run queries over it to look backwards and say, this process is known bad, or this IP address is known bad. Show me everything associated with it. Let me pull all of the events from this machine, load them up in Excel or some other tool, and start slowly working my way through it. But if I'm responding to an intrusion across 100,000 machines, I can't keep up with this. My team can't keep up with this, no matter how we slice and dice the work. So we realized that it would be better for us, instead, to build a service that, given an IP address that we discover during incident response, or a process name that we know is bad, or some other attribute about activity in the environment, let me write that and put it in the cloud as a signature, and then have my agents sync it down every 5 to 10 minutes. And then next time they see communication with one of these known bad IOCs, I want it to give me a real-time alert. And so this is really effective, right? Once I find my red team's command and control server, I'm going to instrument my environment so that within 15 minutes, every other machine that's calling out to that server lets me know. That is far faster than any MapReduce query that I can write and execute across 8 petabytes of data a day. Furthermore, when I find one of those processes and I take a memory dump, I'm going to learn what their malware looks like. I wish that I could write a Yara rule for that custom malware and then run it across my environment, not waiting for something to execute, but scanning process memory in real time and letting me know when it finds hits. So we did this. And in December, we had a red team engagement that worked really well. We were really happy with our detection coverage along the kill chain. And as soon as we got that first evidence that the red team was present in our environment, this is what we did. So we found the red team. We found the IP that they were using for command and control. And they had several, right? They're good at operational security, so they're not hosting everything behind the same server. But we took this IP address and we added an IOC for it. Within 15 minutes, we were getting real-time alerts left and right from machines that we didn't know had been compromised. We hopped onto those machines and dumped process memory. We took that, reverse engineered it, found attributes about the process memory that was unique to their malware. We wrote a Yara rule for that. We executed that Yara rule across our environment. When we got the results back from that, we then took more memory dumps. We found more network indicators. That gave us additional IP addresses that the red team was using for exfiltration or for command and control. And then we started back at the beginning of the process again to uncover more layers. And so rather than the blue team being, say, 24 to 36 hours behind the red team, slowly doing event log forensics, doing MapReduce queries, trying to build up a timeline, we were receiving more alerts from compromised machines than we knew what to do with. And so now I have a problem that excites me. I need to build the tooling to handle incident response, to handling all of the entities that are coming out of my incident, keeping track of which tasks have been performed, whether I've done forensics on all of them, what the remediation actions are. I'm finally at that right side of my blue team kill chain. So what I've learned in all this is that there's a maturity model that I have slowly gone through, and I want to share it with you because maybe you can identify with it and spot where you are in the process. So we started off with inventory, right? If you don't know what machines are part of your infrastructure, if you can't point to them and say, give it an IP address or a machine name, and this is mine or this isn't mine, then you can't be effective anywhere else here. in this pyramid. Once you know which resources are yours, do you have telemetry from them? Are you getting activity from all of them? Would you know if one of those machines stopped reporting? Next, given that telemetry, do you have a system in which you can do detections? I'm not talking about amazing, sophisticated ETW detections for process injection. Can you just pick some behavior that you believe is against your business policies? Maybe a logon as a service account. Maybe a login from an IP address that isn't part of your organization. Can you detect that? If so, as you start to build these detections out, can you handle the triage burden of this? As you scale it out to an analysis team, have you written down what they should do for each event? Why you wrote that an analytic in the first place? What maybe forensics actions they should take if they get what looks like a true positive alert? Well, if you can scale out triage and you can do detection, then now it's time to start thinking about the actual threats to your business. And again, this is threat intelligence, not hashes and IPs, but actors, campaigns, conflicts with your business goal, and the tools and techniques that those actors use. Well, if you can understand those tools and techniques, now you can start detecting behaviors associated with these adversaries. For us, this was the shift from successful logins and process starts to processes that are communicating to unknown places, threads being created in other processes, things that actually correlate with real adversaries, not just our red team, and not just the data that we happen to have laying around. Finally, if you can do that, you have the data, you know what to look for, then you can hunt over that, right? Because you probably aren't afraid now to get a true positive alert, and you might have missed something. While you were building this stack, an adversary may have used these techniques 2 weeks ago before you had the detection for them. So go look back in your data and see if you can find evidence of a latent compromise. Finally, and this is where my team is pushing into right now, once you've found something, you're hot on the trail of the adversary, you've experienced an intrusion, can you track them just as quickly as they can move around your environment? Right? And that's about reducing that blue team kill chain so that you can evict, not just detect the adversary. Finally, if you can detect that adversary, you can find out where he is, can you act rapidly enough to regain control of your environment before he gets to your business's crown jewels? And if you can do that, go tell the world, right? Share what you've learned. Share the adversary campaigns that you're experiencing. Share the analytics and the technology that's working or that hasn't worked with your trusted partners like I'm doing today so that we can fight evil and so that good can win. And this naturally leads itself to a capabilities model or a maturity model, right? I started off in the bottom. We were detecting lots of hygiene issues and we were proud of ourselves that we could see people who had maybe forgotten to change their password or who had a scheduled task running, failing to log on every hour. And eventually we moved our way up. And now our red team has to adapt their techniques because they see our effective blue team coverage. And so we're starting to detect our red team across all phases of their kill chain, and we're starting to make them respond. And then finally, the demo that I gave you at the end of using IP IOCs and process memory Yara rules allows us to operate at the same tempo as the adversary, which is really where I want to get to. I would love to chat over the next couple of days if this interests any of you. On the bottom right is a link to the ETW library that we wrote. We've got sample code there so that you can get your own little sysmon or your own little Defender ATP running within 15 minutes, whether you're a C# or a C++ developer. And then the IR hierarchy has proven to be quite popular, so if you'd like that, you're welcome to have it too. Thank you.